started to learn about some specific terminology of 5G, like verticals and horizontals, and what is different and what is similar between 5G and the former generations. So this afternoon, it's basically the second part of this introduction to the course, and we are going to talk about topics that are of a horizontal nature. So these are technologies which potentially you could use for any of these vertical scenarios we discussed this morning. So this afternoon we move more into technology. Okay. Now there are a few, as you see, categories of techniques which are considered of relevance to 5G. Okay, they are very diverse between them. They tackle different aspects of communication networks of the future. They are different in nature. Of course, they are not completely independent, so somehow they also collaborate, right, between themselves. So we do have, for example, you see massive machine communications. So this would be many devices transmitting in the same area. So you could think, for example, about massively deployed sensor networks. Okay, so when we say machine, you immediately have to think about something different than the device as we know it from 4G and before. So machine really means something like a sensor, right? Something like sending potentially low data rate and having requirements that are in nature different as compared to broadband. Loosely speaking, sensors, but you can also have actuators, right? So not only sensing, but also basically controlling some system, right? So it is a bit beyond the normal definition of wireless sensor networks we are used to. So another basically aspect, it's that of moving networks. Of course, we do have mobility supported also in 4G and before, but here you start to talk also about, let's say, situations where you do have very high mobility. Okay, so you do start to talk about vehicular networks. It has been there as a research topic for a while, but for the first time you are starting to integrate this into the mainstream cellular communication. Okay, so you do have things like, as we saw this morning, vehicle-to-vehicle communication, vehicle-to-infrastructure, intelligent transportation systems. Okay, this has been part of the smart city framework in the last few years, but now it has been taken into account seriously by mobile telecom industry and research. Okay, you do have ultra-dense networks, which are basically the evolution, if you will, of what in 4G was called heterogeneous networks. So you might have heard of heterogeneous networks or HETNET, where you do have basically the normal macrocellular network deployment, and then you have another layer of deployment, which is called, we used to call femtocell, or some people, I mean, depending on the range, you can have picocells, microcells, but in general, we talk about small cells, right? Now, ultra-dense networks are, in a sense, following the same trend. So you do have the coverage provided by the macro cell system, and then you have some dedicated, say, high-capacity hotspots provided by the small cells. You go beyond this definition with ultra-dense networks in the sense that you assume a lot of access points being deployed over some area. What does it mean, a lot? It means more, potentially many more, much more than the number of devices connecting to the network. So you move from a situation where a base station would always have like a user to serve to a situation where potentially it's not true anymore. So there is a kind of, in the sense, in 4G, there was a scheduling problem in terms of picking which users you have to serve with one base station. In ultra-dense networks, it's a bit reversed. So you might have to pick which base stations you have to use to serve one user. Okay, so it's different in nature. And we're going to see later in the course there are many interesting results and a lot of interesting work being done in ultra-dense networks. And I'm aware of a good research thread here, okay, in IIT Kharagpur about that as well. Device-to-device communication, it has been there again for a while. So some of these areas will not sound very new, and I agree with that, but it's the first time they are considered all together, okay, as far as I'm aware. So device-to-device is an alternative to ultra-dense networks, again providing some extra capacity, some, providing some help to the network to offload some traffic. So along these lines, there is also the integration of LTE, for example, network with Wi-Fi, right? So when there is a surge in demand, you might think as a mobile operator to offload some of your traffic, so some of your users, to a Wi-Fi network. You could do the same thing in nature. I mean, it's a different way to address the same problem with device-to-device, right? If you don't need to go back to, let's say, the common point, which is the base station or the access point, you could let the devices manage by themselves, right? So you do have transfer of data between the devices. This also fits, in a sense, is similar in nature to what you do with another concept which appears in LTE advanced networks. It's called phantom cells, where you do have, again, a macro base station providing the control plane service, and then you have the small cells which are providing the data plane. They only have the data plane. So the macro cell would have both control and data plane, and the small cells would only have data plane. Okay, and they rely on the macro cell base station to get the control information. Okay, similar story with device to device. Okay, we are not going to touch device to device in this course. I have to select some topics and go deeper into that, but it is an interesting area of research. And for example, in my college in Ireland, there are a few people working in this area. So it's a rich area if you're interested in doing some research as well. The last one of these ovals you see here is ultra reliable communication, which I mentioned again shortly this morning. This is about basically having communication systems that potentially never fail. Of course, that's an idealization. Things that are built by humans fail, right? Not even machines are perfect, but you tend to have basically a very high reliability, right? Something like 5 nines, 6 nines, so almost always working. Yeah. Now this is kind of, if you will, we could say it's sort of general helicopter view on what's going on in 5G networks. Now, how do you fill out these ovals here? Okay, you fill them out with specific technological solutions. Okay, so it's kind of a multi-layer approach. So you see, this morning we talked about the general application areas, right? Transportation, health, industry, automation, whatever. And there are a few possible flavors you can give to your network to do that, and then you have to enable these flavors by using some technological means, right? And most of the course will be about, I would say, how you actually make sure to realize what's in this slide, more or less, okay? Part of the course is also about, okay, there are two components in this course. One is about the design, so to actually come up with algorithms, with signal processing techniques, schemes that solve some problems. Another part will be more of an analytical nature, not analytical in the sense of equations. There is a bit of that, but it's more in the sense of understanding the network. So we will see some tools to analyze network performance or to model a network. Okay, so there is a bit of this more descriptive endeavor, and then we have also the proper engineering design. So there is a bit of both. So there are a few things you can do, okay, to provide these different requirements. You can get more spectrum. Okay, we'll see how you could do that. For example, you could have this MultiRed. MultiRed simply means that you do have the possibility to interwork between networks. So it's not just LTE working on its own and hoping it doesn't mess up with other systems and vice versa. You try to combine the things and maybe help each other, right? So if there is a surge in capacity and you do have a Wi-Fi network available, why not offloading some of the cellular traffic to the Wi-Fi network, right? In the past, it was more of a fight, as far as I remember, and cellular, actors wanted to sort of kill Wi-Fi or compete with Wi-Fi. I think it has changed, and there is a smarter approach. Now it's about using it, okay? Multi-layer network, by this I mean heterogeneous networks, basically. So you do have different layers based on the coverage range. So there are macro cell networks, which cover a few miles, say, and then you have micro, which are more urban base stations. So you would have coverage up to a few hundred meters, maybe up to half a mile, something like that. And then you have femtocells, which are basically, picocells, which are covering, say, up to a couple of 100 meters. And then you have femtocells, which are like Wi-Fi, so they are up to 100 meters. That, it's going on. So it might be even smaller cells, but that's where we are at the moment. Multi-node and multi-antenna transmission. So this refers to the possibility to either create virtual arrays of antennas. So multi-node would be something that is called in LTE Advanced coordinated multipoint. It has different name, network MIMO, virtual MIMO. You pick the one you prefer, but the idea is that you have a multiple antenna scheme, which is just logically a multi-antenna scheme. Physically, it's not. So you do have different radiating elements in different positions, and you kind of combine them, okay? Possibly connecting them through optical fiber, for example, and then you have a central unit processing things, okay? Some people call this Cloud RAN, Cloud Radio Access Network, so it has different names. And then you have the more traditional approach where you have all the radiating elements in the same place, co-located. But the difference in 5G is that you go up with the number of radiating elements. So in LTE, you probably go up to 8, 16, more or less, at the base station. In 5G, they're talking about hundreds, okay? Now, one smart thing they are realizing now in the physical layer MIMO is that in the past, they simplified the problem, and they said you can have many antennas everywhere. The truth is, it's very difficult to accommodate many antennas in a small device for a few reasons. Complexity. Every antenna needs a dedicated RF chain, and the more antennas you have, the more complicated is your signal processing, which is bad also for power consumption, right? So it's not good for a handheld device, for example. Another thing is physics, okay? So there is a need to basically position antennas on a device with a certain distance, okay? So this distance is roughly given by half the wavelength. So the wavelength actually, as you know, is given by the speed of light divided by the carrier frequency, right? So the higher you go in frequency, the smaller your wavelengths become. And so potentially, I'm not saying it's always true, but potentially you can squeeze more antennas. Now, if you do the math, at the frequencies we basically use normally for cellular communication, it's complicated to have more than one element, right? Because it takes some separation distance. And so what they are assuming in 5G is to avoid this assumption and to basically move all the complexity at the base station, where you don't have much of a computational limitation, you don't have much of power limitation, you don't have much of a cost limitation, and you don't have much of a space limitation, right? You have a huge tower, it's yours, you paid a lot of money. I mean, the biggest problem is to get, right, the real estate and to cable the thing, but once it's there, why not use it? Mobile phones is different because you cannot ask people to pay too much. You cannot ask people to have a mobile that runs out of battery very quickly. So the idea is now to move, in a sense, all the complexity at the base station, and you don't assume normally, at least in current research, more than one antenna per mobile phone, which is good, right? Situation might change when you go into millimeter wave. Millimeter wave are frequencies that are in the range of 30 to 60, definitely. Some people talk about further frequencies like maybe 70, 80 gigahertz. So it's definitely anyway an order of magnitude higher frequency than the normal sub 6 gigahertz frequencies we use in cellular communication. So if you go higher up by a factor of 10, it means that your wavelength reduces by a factor of 10, right? We remember that lambda is c over f. So if f becomes 10 times bigger, lambda becomes 10 times smaller. So then you might not have that problem we were talking about. But this is in the experimental phase, right? So it won't come tomorrow, but might solve this issue of having a proper MIMO system where you have multiple antennas at the base station and multiple at the mobile phone. Radio link concepts, I mean basically other PHY techniques. So you do have advanced coding schemes being investigated, like short frame codes. LDPC has been there for a while, so I don't consider it really so new. And then definitely new waveforms. We're going deeper into that later in the course, but the idea is that you basically move away from one waveform for all the network, okay? And you start to have a set of options, depending on what you have to do. Why do we need that? We go back to the first lecture where you don't have a single scenario like we used to have in 4G. A lot of data rate for smartphones. No, it's not like that anymore. So you do have very different requirements. Therefore, you need to tailor, right, your system to fit the requirements, right? This morning we talked about service-aware networks. That's the idea. You have to tune your network so that the service is happy. Not like in the past, that the network is what it is and the service will somehow cope. That's not the way you want to progress, right? So you want to, I mean, there are some requirements because of e-health, because of transportation, because of vehicular networks, and the network should, in a sense, adapt to all of them without designing a dedicated network for its application. That would be crazy, right? Because in 5-year times, I'm sure you can add to that list I made this morning. What do? Do you design other 5 or 6 networks? It cannot work, right? So you do need a sustainable path in the evolution of the network, right? So you do want to potentially use different solutions and use them when you need them, okay? So in terms of the waveforms, for example, if you have a scenario more or less like today, OFDM is pretty okay. But if you start to have a scenario with a lot of devices that are very close by, then OFDM would probably crash at some point. And that's why people are doing a lot of work in alternative waveforms. To name a few, GFDM, filter bank multi-carrier. So GFDM stands for Generalized Frequency Division Multiplexing. Filter bank multi-carrier, BMC is another one. Then you have Universal Filter Multi-Carrier, UFMC. They are all sort of related, but they are all different. So depending on what you want to get, you will pick one or another. But what they have in common, generally speaking, they have looser synchronization requirements compared to OFDM. OFDM is very good, provided that the network is synchronized. If you start to have problems in synchronization in time or frequency, OFDM is not good. And another problem with OFDM is not particularly good in terms of out-of-band emission. Normally, the decay of the signal in spectrum is pretty slow. And what happens is that if you have systems nearby that are using the adjacent bands, you start to interfere a lot. And again, this is a scenario that doesn't, I mean, this is a solution that doesn't really appeal when you have a lot of devices co-deployed, right? Like sensors, small cells. So there is a feeling that OFDM is okay for something not much beyond what we do nowadays. It won't be okay anymore if you evolve the technology further, okay? If you have new scenarios we didn't envision during 4G design. Okay, at a glance, that's the picture, and it has a lot to do with what I'm going to say in the course. Now, just a sort of, quick mapping between what parameter you're trying to optimize and what technology efforts are being made at the moment. So that's a photograph, if you want, a snapshot taken now. Things might change, right, with time, but you see there are a few requirements, like, for example, if you want to minimize the latency in the air interface, then you do have new multiplexing schemes. For example, one thing I'm not going to talk about, but it's a very interesting research topic, is called full duplexing. For full duplexing, what full duplexing does is that it, normally in cellular systems you have two options to separate the downlink and the uplink communication. Either you use what we call TDD. So TDD means time division duplexing. So you do have a time slot for downlink and a time slot for uplink, right? And that's how you separate them. Or you do FDD. which is frequency division duplexing. So you do have one frequency for downlink and one for uplink, right? What they try to do, and they are actually accomplishing more or less with full duplexing, is to have the same time frequency tile, same resource, used for both downlink and uplink. The main problem with this technology is what is called self-interference. What happens is that when you transmit, part of this is going to impact your receiver, because the receiver is also active, right? The same time, same frequency. So this is coming back in a sense, right? It's returning to you. And they are developing self-interference cancellation schemes, so they're working on that. Okay, so we are still far from the promise of having twice the spectral efficiency they are claiming, but there is work going on. Okay, another example, say, let me think, something representative. Say spectral efficiency. Okay, so here you could have, for example, different MIMO schemes, right? So a good thing about this massive MIMO is that it kind of boosts even more the gains you were having with MIMO anyway. Okay, so you do have a big boost in the spectral efficiency. Other thing you can do, let me see, connection density. You could basically manage the increase in density of devices transmitting in the same area by using. You could cope with it by using new multiplexing schemes. For example, what we were saying before, filter bank or GFDM. Okay, so alternatives to FDM, for example. So you do have, actually, when I say new multiplexing, you do have two things. You have the modulation proper, right? So you do what will substitute to FDM in a sense, and then you do have the duplexing between uplink and downlink, right? Full duplex, half duplex, and so on. So there are. I'm not going to spend too much on this because it might be a good exercise for you to start to map this and start if you can see. Like a good question for the exam. Now I might not give this, but it would be to to tell me. It's going to be multiple option the exam, but I could give you, for example, a certain set of these mappings and tell you which one of these is the reasons why there is this mapping. So there is a reason. Okay, there is a reason behind each of these mappings, and up to you to find out. I think I gave you some hints, but it's a good exercise to think about it. Okay, this is a very packed network. I don't want to spend too much, but basically a very packed slide. Sorry, but just to give you some take-home messages. So you'd see that between today and the future, you're going to have many more small cells, right? You're going basically to have a much more predominant role of spectrum sharing, okay? Not only between operators in the same system, also with other systems. So we're going to see later in this course possible approaches to share radar bands. Okay, so radar bands are good because there is a lot of spectrum available in good regions of the EM spectrum, so below 6 gigahertz, and they are not exactly used very efficiently. Duty cycle is low. Another thing is that radar systems are very directive, and the SNR condition is very good, right? So it's possible to coexist with this system without disrupting their operation and still using a lot of band for commercial application. So there are a few groups working on this, and not too many though, and we are one of those groups. Anyway, I'm going back to that with a few lectures later on. Let me see. Yeah, integration with Wi-Fi is something that has changed. I think in the past there used to be LTE and Wi-Fi kind of, they're together in a sense, but not really trying to interwork. Okay, now the situation is different. There are even other approaches to spectrum sharing, like what we call LAA or LTE unlicensed, LTE-U, or LAA, which is licensed assisted access, which means you use the Wi-Fi band for LTE operation. Okay, as simple as that. Right now, the operators don't basically like the unlicensed band, right? Because it's free for all. So there is no QoS guarantee, right? Any system, even your microwave oven, uses that, right? Many systems. So, but what they are trying to do, for example, enabled by this very directional capability in the transmission given by massive MIMO, you can get rid of some of the interference problems, right? So if you have your user, you focus all your energy in that direction, you don't care too much about what's going on in the rest of the area, right? So there are solutions in 5G that enables new spectrum to be used. Another approach is what is called license shared access, LSA, and it's called, I think, SAS in US. So this again is a sort of spectrum sharing where you basically provide some quality of service guarantees. So for example, there is an incumbent using some spectrum, say a military, not military, say radio location, for example, service or missile tracking, or what are other examples? So like this, what they call public making special events, like wireless microphones, right? So basically what happens in this LSA spectrum sharing regime is that there are few tiers of systems. So there is the tier 1, which is the licensed. It's like cognitive radio in a sense, but in a practical scenario. So the first tier would be the licensed systems, the systems that own the license. They do whatever they want. Now, when these systems are not active, you have an agreement with some second tier systems, which could be, for example, mobile operators, where they pay a fee, and for a certain duration of time, a certain band and a certain area, they are guaranteed nobody else is going to use it. Now, this is being enforced by the government in some places. Okay, in Europe it's picking up. So basically, you can keep your band if you are an incumbent, like say a wireless microphone system, but if you don't use it, you have to allow other systems to use it. The difference compared to cognitive radio, which might, I mean, this might ring a bell in many of you, but there, as cognitive radio, but there is a difference. Cognitive radio was opportunistic in nature. You kind of sneak in, right? You sense and you try not to disturb the incumbent. Hopefully, it won't complain. This is different. The incumbent is fully aware you're there, and in a sense is getting some compensation, or at least, even if it doesn't get money, it will get the possibility to keep using the band. Instead of getting it back, the government say you can use it, but somebody else should use it as well, right? Because you're not the only one that needs spectrum. And during that time, in a sense, at any time, either the incumbent or the secondary system would have quality of service guarantees. That's a big difference compared to cognitive radio. Okay, so there are many things going on. I don't want to spend too much time on this because we're going back to this in the course. Yeah, so of course many more advanced physical layer technologies like massive MIMO, millimeter wave, new waveforms, full duplexing, ultra dense networks, and all over IoT playing a much bigger role than it used to. So Internet of Things, in my understanding, is picking up as one really to be as important, if not more, than the traditional mobile broadband work. If I just look around, the researchers I know and the work I'm aware of, in my head it's like taking about 30 to 40% of the share right now of work, okay, of funding, of investment. And I think it's not going to stop. It might be at some point that the mobile broadband, which was dominant so far, won't be really the biggest share of the market anymore. Not happening yet, I think. I don't have numbers, but my gut feeling is that the things are going to change. Okay, so if you want to consider a research topic for your projects, might be worth to start to look into something else than traditional LTE plus things. Okay. There's a lot going on with this machine type communication. I started myself to look more into that, okay? Of course, you can do good work still in mobile broadband, that's okay. There are many things you can do, but my suggestion is to try to keep an eye on these alternative machine type networks, because many things are going to be happening there in the next few years. Yeah, so basically, that's kind of the architecture of a 5G network at a glance. There are a few things like, some scenarios defined by some projects. Now, a very good European project that has been doing a lot of fundamental work in defining the architecture and scenario and also technologies of 5G is called METIS, M-E-T-I-S, and they now have a new project running. It's called METIS 2. So if you want to have a first idea about 5G and the requirements, I suggest you look into that project. Okay, the phase 1 has ended. Now they are in phase 2, I think, and they did a lot of very good groundwork. In a sense, they make it easy for you, because many of the scenarios, the requirements have been identified by these European projects. So it's kind of landmark project in 5G, at least as far as Europe is concerned. Yeah, so you see, for example, in the same network you have different things. You have Cloud Run, you have this coordinated multipoint, which is this different base stations coordinating to form a virtual MIMO array. You have ultra reliable communication, you have device to device, you have massive MIMO, so many different things blend in. And some things that are happening, of course, data rates are going high, inter-site distance is going very low. So with these dense deployments, now you really have every about 10 meters potentially a node. I mean, I'm not saying right now, but it's kind of an outlook in the next few years. And other things, I don't have too much time to explain right now, but have a look and try to see how the different actors blend in one picture. Any questions so far? Comment? Yeah, let me know. Okay, anytime you can just interrupt me if something doesn't make sense, or you have any doubt. So again, going a bit more into detail, what are the R&D technology areas that are relevant to 5G? So there are some things that started in LTE Advanced. Some things are kind of in between. So it's difficult to draw perfect lines. So some things have been going on, being evolved upon. Some things are definitely new to 5G. So for example, multiplexing schemes, they are not within the LTE Advanced framework. Okay, they are considered something else altogether. So they are going maybe to be standardized, but that will be the next wave of standards. Okay, while some other things like beamforming and advanced MIMO schemes, they could make it actually to the later releases of LTE Advanced. Okay, millimeter wave starts to be already something considered more of a 5G nature, and then new coding schemes are again a bit more far-fetched. So the more far-fetched you are in terms of the research, the more is going to be pushed beyond LTE Advanced. Okay, and so it will take a few years before it actually makes it into the standard. I'm just going to give in the last quarter of an hour in this lecture some like general overview of some technologies areas. So these are kind of ID cards almost. So I'm going to give you some snapshots, okay, about these technologies, and just to make you aware who they are. And then later in the course we are going to take some of these and look more in detail into these. So millimeter wave refers to higher bands. So conventionally we are talking about 28 to 31 gigahertz or beyond 60 gigahertz. Yes. Sure. Yeah, again, my understanding, this is like more to do with channel coding. So there are some people working, I'm not an information theorist, so I tell you what I know. They are working on short frame codes. So if you look into the channel coding theory, that is mostly related to the consequence of Shannon work. Shannon started to lay down the foundation, and then many people worked on that. So it's based on the assumption that the length of a code, so many bits in a sense you have in a code word, tends to infinity. So the results of coding theory are based on that assumption. Okay, so the bounds they get, the capacity and so on is based on that assumption. Now if you want things to be fast, you possibly need new codes which are shorter in length. And the idea here, I mean, you already have shorter length, like you don't have infinite blocks, but there is no theory. So what we are doing now, we are kind of reverse engineering and try to find some codes that work. But the theory itself is asymptotic, right? But if you want better codes that are potentially, becoming, getting the most you can out of, the code itself and becoming very fast and so on, you need a new theory. You need a theory that is not asymptotic. You need a theory based on code lengths which are short. Other schemes that are, I think they are not so new, but people keep talking about them, is LDPC, low density parity check codes. I think that has been there. Honestly, I don't know about the standard, but it has been there for a while. And of course, you do have coding also in the sense of space coding. So you do have pre-coding schemes for massive MIMO. So the normal ones people are talking about are zero forcing, maximum ratio transmission, generalized zero forcing. The bound is given by a scheme which is called dirty paper coding. Dirty paper coding, though, is very complex. So it gives you a bound, but normally, at least in downlink, I think the normal choice is to adopt zero forcing, okay, for example. Yeah, so there are a few things happening. It's like in the past that you had like the normal channel coding, and then you had the space-time coding, this like spatial things, and the same is happening now with new coding altogether, new coding schemes in time, and then also you have the spatial coding, right?
Okay, with the new codes, what exactly 5G is expecting from these new codings?
Well, if you have, well, massive MIMO is definitely something that will give you a lot of benefits in terms of energy efficiency. Can transmit at lower power at the mobile phone, and you have an immediate boost given by basically you would add 10 times the logarithm base 10 of the number of antennas at the base station. So it's if you have a lot of antennas, say you have 100, what it means is that you have 10 times log 10 of 10 to the second, right? So it means 20 dB, okay, immediately. So without doing anything at your mobile phone, just enabling 100 antennas at the base station, you can boost the signal to noise ratio by 20 dB. What does it mean? That if you want to get a signal to noise ratio of 25 dB, which is very good, you just need 4 dB in your mobile phone. That's one practical example. There are many, okay, others we are going back to massive MIMO later on, but about the actual channel coding, I know there is work going on, okay, with these short frame codes. I cannot comment myself because I'm not an information theorist, okay. I think the idea, again, is to get fast communications, okay. You want to be fast, okay. So if you have to wait long blocks before you process your data, you're not fast, you're not real time. If you want to push things towards real time, you need codes that are optimized for short lengths. The problem with current codes is that the theory, it's all about asymptotic block length, infinity. And then you kind of come up with something that works. But if you want better codes with shorter lengths, so with shorter code word length, right? Shorter number of bits you have to process in one batch, you need a new theory. Okay, I'm not fully familiar with I know there is work going on, and I think they're trying to accomplish this. So for this kind of channel coding schemes, it's more, I would say, the responsiveness. You want to be fast in responding, real time kind of things. In terms of massive MIMO, there are a few, and one of them is you can basically reuse the spectrum better because you're very directional. So if I transmit to my user in one direction, I will not disturb another user, so I can create another beam, and potentially could have all the users using all the spectrum, right? So you don't need frequency division multiple access anymore. So that boosts the capacity. Energy efficiency, it comes from the array gain, which is if you have a very large array, you have a very large SNR gain. Okay, 2 examples. There are more. Okay, so there are good reasons to do work in new coding schemes. Okay. Any other question? No? Yeah, feel free to ask and interrupt. Yes.
Sir, the previous slide, there is a distributed mobile code functions.
Yes.
So what does that distributed mobile code do?
I think you're talking about this one, yeah? So this mobile core distributed functions. I think in general what they refer to, basically you try to distribute functions over the network. So there are 2 approaches, I think, okay? One is more of a centralized nature. One such example is Cloud Run. So you do have your radiating elements, which are pretty dumb, remote radioheads, they call them. They just do DRF, okay? and then all the processing is actually happening in a central unit. That's the opposite of distributed. Distributed, as it happens today, is more the case. So you do have most of the functionalities and the processing in the base stations, okay, at the edge. Even more so, probably if you have dense deployments. You cannot imagine to have too much of a centralized approach in that case, because it would be simply too much information to process. So there is some person back in my college used the metaphor of a slider. So you do move the intelligence back and forth between the edge and the core, depending on what you have to do. So what I'm talking about is mostly wireless, but you have the same hierarchical situation with the optical networks, right? You have the so a base station would connect to an optical network unit, and then again it would go up sort of as a tree, like a tree, and connect to an optical line terminal. So again, you know, depending on where you put your intelligence, you have different solutions. Now, for example, Alcatel-Lucent has been proposing something even in between. It's called mid-haul. So you have the backhaul is the situation where you have intelligence in, say, in a base station, and then you have the connection to the rest of the fixed network. Yeah, that's called backhaul. Front haul would be this cloud run thing. So you do have radiating elements, and then they are connected to a processing unit. So that's what we call front haul. Now, backhaul means all intelligence is in the base station. Front haul means basically all the intelligence is not in the radiating element. It's in a central unit. Mid-haul is in between. So they call it phi-mac split. You can put the phi in one part, mac in another. So there are a few things you can do. And again, what are the factors involved? Cost, how fast you want to be, capacity, right? There are different, I think the delay is a very big factor, right? And also like how much information you want to exchange. I think something like Cloud Run is okay as long as you don't have too many radiating elements. If not, it becomes really complicated to process everything and provide a real-time response, right? And for dense deployments, I feel might not be the best option. But you know, it's the way you would do, for example, coordinated multipoint, right? So for multiple base stations coordination, that's fine. So again, it depends. Any more questions? Yes.
So for a ultra-dense network,
yes.
so as the network densification increases,
yes.
the interference also increases.
Correct.
So how can we get high network capacity?
Yes. It is an interesting question and an interesting problem. So of course, as Kartik is saying, there is a catch, right? You cannot just increase the density and hope everything will work out, because the closer you get in terms of electromagnetic radiation, the worse it is, right? The wireless medium is broadcast, right? So you transmit everywhere, not just to your intended receiver, also to the unintended receivers, right? So you, in a sense, you screw up the communication. Of course, there are solutions. I mean, you could try to do so. We did some study seeing what happens if you have frequency reuse, right? I'm going to show a bit of that later in the course. You could use the spectrum dimension, right? You could start to coordinate the spectrum usage within these cells. A problem there is that normally the way you do it is pretty static and regular. So you have macro cellular deployments, and you do this honeycomb kind of allocation, right? You see it in textbooks on you know, GSM and so on. So they do frequency reuse in a certain way. That is okay for deployments that are more or less regular. If you start to have very random deployments, like small cells, that will not work out. So there are probabilistic versions of that. For example, one is what is called frequency aloha, okay, and others. Okay, I'm going to present some of these later on. So you can do two things, I think. Mostly you could do frequency coordination. Possibly, especially if you go into the millimeter wave domain, I think you can use a lot of the benefits of massive MIMO. So if I transmit very directionally, most likely I won't interfere with you, unless you're really unlucky, you are along the same line, your user is along the same line. You see, probabilistically that won't happen, right? So there are a few things you can do, but you're right, it's a problem. Okay, so it has to be taken care of. Mostly, I think now people are looking into the performance bounds. You know, these ultra-dense networks, as you know, it's new. So we first have to understand the bounds, the basics, and then people are slowly moving into MAC. Okay, how you actually make sure that you get to the bounds as close as you can, right? Okay, so I think I'll move on, because we are running out of time a bit. Okay, so there is millimeter wave, where you have basically you can enable very high data rates. Why? Because you have a lot of band available, simply, right? You can have a few gigahertz instead of few, maybe tens or maybe 100 megahertz as you have today in lower bands. You multiply that by 10, Shannon equation, bandwidth times logarithm of something goes up linearly. Not so true, as you know, because the noise is also going to increase, but up to some point you get a pretty good increase, right? Basic question: what happens if you increase the bandwidth to infinity? Is it always good? In terms of capacity, what happens? Anybody? It's a textbook question, okay? So power, if you're alone in the universe and you transmit to your user, increasing power is always good, right? Now, if you have other systems, of course, interfere. What happens if you're alone in the universe again and you transmit with increasingly higher bandwidth? Is it always good? We even have a number. Very good. So it's basically there are diminishing returns, right? Some there are like proofs, right? There is a proof in books, and it basically saturates. So, but in general, you have really to transmit very large bandwidth before you hit that cap, right? So it's good to have more bandwidth. Small cells. I mean, there is a. The reduction in the size of a cell leads to different concepts also in the definition of a cell itself. So we are kind of moving away from the concept of a very well-defined cell and into something that is a bit more like soft handover, right? So you do see in this case, for example, you have this like you see a user served by multiple cells. It could be an example of coordinated multipoint, and as the user moves within this dense deployment, it would get basically served by other access point. But you see, it's difficult here to have a clear-cut picture of a cell. It's more like a continuum, right? More soft definition. So it's more like user-centric, really, rather than cell-centric. So a big difference in many respects, not just cell definition, also in terms of requirements. It's much more moving from the network to the user. Okay, the user is the important guy, right? And the network should obey. Again, service-aware networks, right? Same concept. Modulation. I'm just going to close now. We're going to, pick up on this tomorrow. So you do have different ways to do modulation. So we are trying to basically get rid of high out-of-band emission due to the characteristics of OFDM. For example, with filter bank, you can get much lower out-of-band emission, which is good for sharing the spectrum in a certain confined scenario. Device to device, we already said. So, of course, again, same story as with small cells. You increase the spectral efficiency, right? Because you are reusing the resource for more users, right? So the base station will go about its business, and in the same time, the device-to-device communication will happen in a local region without disturbing, the macro cell communication, and you increase the capacity. If you increase the throughput in the same spectrum, you increase spectral efficiency, right? Not too difficult. We already talked about this a bit. So interworking with Wi-Fi, it is happening. So you can have either a co-located base station access point or not. So definitely there is an integration between the different networks. Massive MIMO, we're going much more in detail later in the course, but you do have the possibility to be very directive with your beamforming, and you see many radiating elements, hundreds potentially. And the rule of thumb is that you should have 10 times the number of radiating elements than the number of users, right? Another option to do interference management is called interference alignment. So it's a multiple antenna scheme, making sure that you kind of minimize the interference from the other cells. Again, I'm not going into details, more information theoretical, but there is work going on in this domain as well. Okay. So what about the future? The future is about few possibilities. We don't know at the moment, so it can be either what has happened before with LTE, like more of an evolution, right? Few amendments. It can be like a revolution with technologies that are very disruptive. I don't believe that will be the first step. For example, you replace the access scheme altogether. OFDM, you change it with, I don't know, GFDM. And that will change a lot of things, even the mobile phones. Or it might be complementary technologies like, of course, Wi-Fi, why not? Device to device. So I would believe it's more of a combination of these two. Revolution normally doesn't really help in technology. I mean, papers, you can write whatever you want, but practically, it will be smoother, okay? So just to give you a last picture, I'm going to go back to this, last part of the lecture tomorrow, so we don't worry. This is just a picture to give an idea of the deployment. So you see that deployments of LTE and any technology, they have a sharp increase at the beginning, and then they saturate. Yeah. So at some point the technology gets mature, and then eventually actually will drop. Right. It will be surpassed by something else. 5G, these are just estimations. It won't be any different. So in the beginning you will have a sharp rise, and at some point it will again peak. But you see that here we are still far from that. Okay. And so there is always kind of a technological life cycle, right? In the beginning, it's very fast increase in the number of deployments. It peaks, it reaches a plateau, and then it slowly decays, as it's happening for GSM. 3G is still, I think, kind of is in the saturation phase. LTE is in kind of the final, it's kind of picking up still, and so it's in a sense reaching a flex point. And 5G is still, of course, in the very early part of the curve. Okay, so they give me abundant signs I should stop. So I'm finishing here. So we'll pick up on this tomorrow. Okay, thanks.